MRI machines are one of the most impressive medical innovations of our time. They allow us to look inside the human body without invasive surgery, providing clear, high-resolution images of soft tissues that are often invisible to other imaging methods. But have you ever wondered how these complex machines actually work? How do they create such detailed, accurate images using only magnets and radio waves? In this video, we'll break down the science, the technology, and the various components of an MRI machine. An MRI machine is a complex device composed of several key components, each playing a critical role in generating detailed images of the human body. At its core lies a large, powerful superconducting magnet, which produces a magnetic field approximately 40,000 times stronger than that of Earth. This magnet is constructed from coiled wires made of a niobium-titanium alloy, a material known for its superconducting properties. When an electric current passes through these coils, they transform into an electromagnet, generating an exceptionally strong magnetic field. The niobium-titanium alloy is classified as a superconductor because it exhibits zero electrical resistance when cooled to an extremely low temperature of -269 degrees Celsius, close to absolute zero. This superconducting property allows the current to flow through the coils without any energy loss in the form of heat. As a result, once the coils are charged, they can maintain a constant current indefinitely without requiring additional power. To achieve the necessary superconducting state, a sophisticated cooling system is employed. Liquid helium, which has a boiling point of -269 degrees Celsius, is used as the cooling agent to maintain the coils at this ultra-low temperature. The entire system is encased in a thermal insulator, which ensures that the liquid helium remains at the required temperature, preventing heat from entering and disrupting the superconducting state. In addition to the main superconducting magnet, the MRI machine includes gradient coils. These coils generate smaller secondary magnetic fields that interact with the primary magnetic field, enabling the machine to produce precise and detailed images of the body. The gradient coils are essential for spatial encoding, which allows the MRI to distinguish between different tissues and structures. Another crucial component is the radiofrequency coil, which emits radio waves to stimulate hydrogen atoms in the body. These atoms, initially aligned by the strong magnetic field, absorb the energy from the radiofrequency pulses. When the radiofrequency stimulation ceases, the hydrogen atoms release this energy, which is then detected by the radiofrequency coil. The signals captured by the coil are processed and transformed into high-resolution images, providing valuable diagnostic information. The scanning process begins as the motorized bed gently moves the patient into the MRI machine. Once inside, the body is exposed to a strong, uniform magnetic field generated by a superconducting magnet. This magnetic field interacts with the hydrogen atoms in the body. Hydrogen is particularly important in MRI because it is abundant in nearly all human tissues, primarily in water, which constitutes about 70% of the human body, and in fat. Hydrogen is the simplest and smallest element in the universe, consisting of just one proton and one electron. The proton spins around its axis, and according to the principles of electromagnetism, a spinning charge generates a magnetic field along its axis of rotation. Thus, the proton in a hydrogen atom creates a magnetic field, similar to a tiny bar magnet. This property is known as the magnetic moment of the proton or the magnetic moment of the hydrogen nucleus, since the nucleus of hydrogen contains only one proton. The direction of this magnetic moment is represented by an arrow pointing from the south to the North Pole. In the human body, the magnetic moments of hydrogen nuclei are initially oriented randomly, effectively canceling each other out. However, when a patient is placed inside an MRI scanner, The powerful external magnetic field causes these hydrogen nuclei to align either parallel or anti-parallel to the field. The proportion of nuclei aligning in each direction depends on the strength of the magnetic field. Hydrogen nuclei can be categorized into two energy states based on their alignment: low energy and high energy. A nucleus is considered low energy when its magnetic moment is parallel to the external magnetic field, while it is high energy when its magnetic moment is anti-parallel. The majority of hydrogen nuclei align parallel to the field, with a smaller fraction aligning anti-parallel. This imbalance creates a net magnetic effect, known as the net magnetic vector, which aligns with the external magnetic field. Once aligned, the hydrogen nuclei do not remain stationary. Instead, they undergo a secondary motion called precession, where they wobble around the axis of the magnetic field, similar to the motion of a spinning top as it slows down. Different hydrogen nuclei precess at slightly different phases, but their combined magnetic moments still result in a net magnetic vector aligned with the external field. The precession occurs at a specific frequency known as the Larmor frequency, which is determined by the strength of the external magnetic field and the gyromagnetic ratio, a constant specific to each type of nucleus. During an MRI scan, a radiofrequency pulse is applied at the Larmor frequency. This pulse causes two key phenomena. First, some hydrogen nuclei in the low energy state absorb energy and flip to the high energy state. This increases the number of nuclei in the higher energy state. And second, the precessing nuclei synchronize, meaning they begin to precess in phase with one another. As a result, the net magnetization vector, which was initially aligned with the external magnetic field, shifts to become perpendicular to it. After the radio frequency pulse is turned off, the hydrogen nuclei begin to relax back to their original state. This relaxation process occurs through two primary mechanisms: T1 relaxation and T2 relaxation. T1 relaxation is the process by which the nuclei return to their original alignment with the external magnetic field. The rate of T1 relaxation varies between tissues. For example, fat relaxes more quickly than water. This difference in relaxation rates creates contrast in MRI images, which can be weighted to emphasize specific tissue properties. In T1-weighted images, tissues with short T1 relaxation times, like fat, appear bright, while those with long T1 relaxation times, like water, appear dark. T1-weighted images are particularly useful for visualizing anatomical structures. T2 relaxation is the process by which the nuclei lose their phase coherence and return to a random orientation. T2 relaxation rates also vary between tissues, with water taking longer to relax than fat. In T2-weighted images, tissues with long T2 relaxation times, like water, appear bright, while those with short T2 relaxation times, like fat, appear darker. T2-weighted images are especially valuable for detecting pathological changes, such as inflammation or edema, where water content is increased. As the hydrogen nuclei relax, they emit radiofrequency signals that are detected by the MRI machine's receiver coils. These signals are then processed to generate detailed images of the body's internal structures. The strength of the signal depends on the density of hydrogen nuclei in a given area and their respective relaxation times. One of the key challenges in MRI is accurately determining the spatial location of the detected signals. In a strong, uniform superconductor's magnetic field, all hydrogen protons in the body precess at the same Larmor frequency, making it impossible to distinguish their positions. To address this, MRI systems use gradient magnets along the X, Y, and Z axes. The gradient along the Z axis selects the specific slice of the body to be examined, while the gradients along the Y and X axes encode spatial information up, down, and across the slice, respectively. These gradient magnets cause small linear variations in the magnetic field strength. These variations cause the Larmor frequency and phase of the protons to depend on their position, allowing the MRI system to precisely localize each signal and reconstruct a detailed three-dimensional image of the body. The MRI machine is a masterpiece of modern engineering and physics. From the superconducting magnets to the gradient coils, radiofrequency pulses, and advanced imaging techniques, every part of the MRI system works in harmony to produce stunningly detailed images of the human body. We hope this video gave you a clearer understanding of the technology behind one of the most powerful medical imaging tools we have today.